Okay, section 16.9 is going to introduce our third model for acid-base chemistry. But before we get into that, we need to introduce to you a new term. Now, covalent bonds, as we've seen them so far, are always made up of electrons that come evenly, one from one reaction partner and one from the other. Oh goodness, I keep having these near sneezes because of the chalk dust. I'm sorry, that's awkward for you to watch. Okay, I'll sneeze one of these days and it will be glorious. Now, if a hydrogen and a chlorine come together to form HCl, we know that this bond got one electron from the hydrogen and one electron from the chlorine. That's an ordinary covalent bond. Well, let's look at let's look at that same kind of perspective, looking at the electrons and how a bond is formed for acid-base chemistry. If I have an H plus ion, that has no electrons. And if I have something like hold up. Yeah, that's right. Something like a nitrate. Oh, let's make it a nitrite. I'll just redraw this. I want it to be a nitrite ion so that it's a weak base. Okay, so we'll have the oxygen, the nitrogen, the oxygen, and a lone pair. So if we have something like a nitrite ion, well, that's going to be in equilibrium with nitrous acid, which looks like this. And it's pretty clear that what's happened is this pair of electrons is going to go and form a new bond with the hydrogen. The hydrogen has no electrons to give because it's an H plus ion. And so this bond right here is formed by an unequal sharing where the oxygen brought 2 electrons to form that bond and the hydrogen didn't bring any. And this is called a coordinate covalent bond. And in some other textbooks they will call it a dative bond, which I prefer if only because it's fewer syllables. So these coordinate bonds are ones where both electrons that form that bond came from a single reaction partner. And they're actually all over the place in acid-base chemistry. Every time you have a Lewis base accepting a proton, it's doing so by donating a pair of electrons to that H plus ion. And so this opens the door to maybe shifting our perspective on acids and bases away from the proton and onto the other half of the equation, onto that lone pair. So a Lewis base is going to be an electron pair donor. This is a reformulation of acid-base chemistry from the perspective of electrons. We call it Lewis theory, and we'll call them Lewis bases and Lewis acids. A Lewis acid is an electron pair acceptor. And I should draw the parallel directly. Remember, Bronsted-Lowry theory said that a Bronsted-Lowry acid was a proton donor and a Bronsted-Lowry base was a proton acceptor. Well, these are really consistent with each other so far because when a Bronsted-Lowry base accepts a proton, it does so by donating a pair of electrons to form that coordinate bond. When a Bronsted-Lowry acid is acting as a proton donor, well, that proton is going to end up accepting a pair of electrons, and so they're consistent with each other. But the Lewis acid-base definition here allows us to investigate different types of coordinate bonds that are formed that don't involve a hydrogen whatsoever. And so let's consider this reaction. If we have BF3 plus NH3, that's going to form BF3NH3. And this will make a lot more sense if we draw the Lewis structures. So here is the boron trifluoride. And here is the ammonia, NH, H, H. And I'll draw these electrons a little bit more carefully because they're important ones. And they are going to form BF3, NH3, and this is the new bond that is formed between them. It is a coordinate bond, and it is formed by the nitrogen sharing both of its electrons. And that means we could look at this and we could say, here ammonia, which we usually think of as a Bronsted-Lowry weak base, is going to act as a Lewis. I'm sorry. Here I'm getting myself all backward. We usually think of it as a Bronsted-Lowry base because of its ability to accept a proton. Well, here it is still a base. I'm sorry. Got ahead of myself there. It is still a base, but now it is acting as a base by donating its electrons. There's no H plus or proton anywhere involved in forming or breaking new bonds in this reaction. And then BF3, it is accepting that electron pair, and so it is actually an acid. It's a Lewis acid. Now this new compound here is called the Lewis adduct. The Lewis adduct. Unlike most acid-base reactions that we've investigated so far, I can't clearly identify a conjugate acid and a conjugate base. They're both the same thing. There's only one product, and so this Lewis adduct is sort of like the mutual conjugate to both of these. Anyway, that's an awkward way to phrase it, so we just gave it its own name. Lewis adduct is what you get when the Lewis acid and Lewis base form that new coordinate bond together with each other and form this larger compound. Now, you may say, well, this is fine, it's a sort of a reaction, but why do we call it an acid-base reaction? It's not going to affect the pH of the solution. It's not going to increase or decrease the amount of free hydronium or hydroxide in solution. So why do we even call it acid-base chemistry? And I guess my response to that is that that's a very Bronsted-Lowry biased opinion that acid-base chemistry must necessarily involve H3O plus or pH or OH minus concentrations. Acid-base chemistry is it's a model that chemists have decided on categorizing reactions according to that model because it's convenient to them, and this is just a different alternative model that is a superset of Bronsted-Lowry acid-base chemistry. In other words, all Bronsted-Lowry chemistry can be described in terms of Lewis acid-base chemistry, plus we now have the ability to talk about reactions like this, identify an acid and a base, and predict a Lewis adduct in a way that is consistent with these simple definitions of electron pair donors and electron pair acceptors. So it seems really strange and unintuitive, and my point is that that's only because you haven't encountered it yet. And to a seasoned chemist, this is just, it is acid-base chemistry. It is because we have adopted that model of Lewis acids and bases, and it's proven useful to us. Okay, well, we're going to look a couple of more Lewis acid-base chemistry reactions in our quiz. So we'll leave it at this as far as the lecture.